Greetings. So welcome to this course ED5330 Control of Automotive Systems. So this course would build upon what we learned in vehicle dynamics, and we would learn more about control systems, and then we'll figure out how to combine both. In designing controllers for automotive systems. Okay. So to begin with, I'll provide a broad overview of the course objectives, and we would also get started with the basic fundamentals, right? So that are required for this particular course. Okay. So what is the broad objective of this course? The course objective is to essentially understand, the process of designing and the design process, control algorithms, or control mechanisms applied to automotive. Okay, so that's what we are going to learn, and with the increasing penetration of control, okay, in today's automobile, I think the tools that we are going to learn would essentially may turn out to be quite useful, right? So I think that's what we are going to look at this. Essentially, if we look at the broad application of this particular course, as we know, in today's automobile, there are various ECUs, right? So that monitor the vehicle state and intervene or take action, let it be the automotive powertrain, or let's say the brake system, or let's say if you take an autonomous vehicle, the steering system, and if you look at improving the ride comfort, vehicle stability, even some aspect of the suspension is also controlled, right? So there are various automotive systems, that are being controlled in an automatic way, right? So in today's automobiles, so we are going to essentially learn the basic theory, behind control systems in general, and then we are going to learn how to apply them through certain case studies. Okay, so that's what we are going to do. So in this particular course, if you look at what are the building blocks of this particular course, first one is, of course, we have learned vehicle dynamics. So we are going to use mathematical models of various automotive systems from that particular course in the design process. We are going to learn quite a bit of control theory. Okay. Then what we are going to learn is that, we are going to combine both and learn the application of these concepts through case studies and projects. Okay, so that's what we are going to do, particular course. Ultimately, at the end of the course, what was one expected to learn? If you look at the learning outcomes of this particular course, at the end of this particular course, we should be aware of various control algorithms, various control design methods, and we should be also have an exposure. We should have also received an exposure as to how to apply those control design methods to automotive systems. Okay? So that's what we are going to learn. So if we look at the overall grading policy, it is going to be quite similar to what we followed previously. Okay?
Sorry, sir. Sorry to interrupt. Are you sharing
please.
anything?
I am sharing the screen. Are you able to see that?
No, sir.
I'm able to see it. I'm able to see it.
We are able to see it.
You can see.
We are able to see
you're
it.
able to see it?
Yeah.
Okay. If you are unable to see it, can you please log out and log in? And maybe rejoin. Maybe that may help sometimes. But I hope others are able to see, right? So.
Yes, Professor.
Yes, Professor.
Yes, Professor.
Okay. So let me just continue. As usual, I am recording the videos. I will upload them through the Google Classroom. And by the way, I have created a Google Classroom page, and I have invited what to say all the participants to that Google Classroom page. But I can see that around only 11 have accepted the invitation. So kindly, the others, I request you to please go to that page and accept your Google Classroom invitation. I think the email would have come to your IITM Mail account. Okay, so please, what to say, log in and then like do that. Okay, yeah, sure. All right. So yeah, continuing on this introduction.
Yeah, I can see now.
Okay, great. Yeah. So continuing on the grading policy as far as this particular course is concerned, what we will have is that like 50% of the course grade will be through homework and projects. Okay. As usual, I will assign the homework either in class or through Google Classroom. But anyway, I will announce it well in time so that you have at least a week to essentially do that. And we'll also have projects where the problem statements and the relevant data are given to you, and we'll help you in doing the process. Okay. So 50% of the course grade will be decided by this component. 25% of the course grade will be decided by a midterm exam. So we will figure out a date later on as we proceed. So we will have a midterm exam that contributes to 25%, and the remaining 25% will be through an end semester. Okay, so that's what we will have. Okay, as far as this particular course is concerned. All right. So this will be the grading policy of this particular course, and what to say. Lectures will be held on Monday, Tuesday, Wednesday, starting at 5 p.m. Unless otherwise, I inform you a priori, right? As far as this particular course is concerned. Okay? And we will use the same Google Meet link, for all the interactions as far as this particular course is concerned, right? Okay. And once again, I will share all the videos through the Google Classroom. Okay, so in today's class, okay, any questions on the grading policy? Okay.
No, Professor.
Okay, good. So in today's class, what we will do is that we will briefly recap some of the concepts that we would have learned in vehicle dynamics, and then we will go forward and then look at some concepts related to control. Okay? So if you recall what we learned in vehicle dynamics, right? So we would have looked at even our domain from a perspective of what is called as dynamical system theory, and we would have looked at a system as an entity to which we provide an input u of t, and we receive an output y of t, right, from the system. That would have been our perspective, right, or visualization of what is meant by a system, right? So with this perspective, we also looked at a certain class of systems. Of course, we looked at a system as a mapping between the input and output, and we essentially wrote down the y of t equals s of u of t, right? So that's something which we looked at previously. And if you recall, we had essentially studied a class of systems, when we did the analysis. So of course, we were looking at what is called as a dynamic system. That is that is wherein all the system variables were varying with time. So time was the independent variable. We were dealing with what is called as a causal system. That is a system wherein the output at any time is dependent only on past and current inputs. That is, these systems are non-anticipated systems. Okay, and then we were looking at what are called as linear time invariant systems. We looked at the definition of linearity and also time invariance. Okay, so linear time invariant was abbreviated as LTI. Okay, So and then like we were also looking at single input, single output systems, right? Abbreviated as system. So this was the class of systems under study, okay, previously, and in this particular course also, like we are going to consider this class of systems as far as analysis and control design is concerned. Okay, predominantly we will be looking at this class. Okay, of course, as you recall, like yes, we are having a lot of approximations or assumptions in this regard. But however, like this class of systems is pretty useful. Okay, like although an approximation, it is a useful approximation. Okay, as far as practical applications are concerned. Okay, so we are essentially going to look at this class of systems. And if you recall, the mathematical model of this class of systems take the form of linear ordinary differential equations, okay, abbreviated as ODE, with constant coefficients. Right? So if you recall, that's what we did, and then we derived mathematical models. We would have applied Laplace transforms to get transfer functions and so on. Right? So, so essentially, I'm sure all of us recall these concepts from our vehicle dynamics course. So we are going to build on these things. All right. So the main objective, like in fact, if you look at what we did in the vehicle dynamics course, was this, right? This is what we did. So, for example, let us say, like when we studied about lateral dynamics, right? So we would have looked at the vehicle as a system to which we provided a steering input, and we would have figured out, like what was the heading of the vehicle, right, or the yaw angle of the vehicle, or the orientation of the vehicle, right, and that would have been considered as an output. So that is what we try to do in the vehicle dynamics course, right? Now, in this particular course on control systems, we are going to pretty much do the opposite problem. That is, suppose if I want my vehicle to follow a desired heading, right? What should be the corresponding steering input that I should provide? Okay, so that's what we need to do. So, in a sense, the problem of control is sort of an inverse problem. Okay, so if you look at this abstract relationship that we wrote down, we can, in an abstract sense, we can say, hey, u of t is S inverse, inverting this mapping, we get S inverse of y of t, right? So, yeah, that's something which we can write down, okay, in an abstract sense. But this is easier said than done. Okay, so it is not very easy to invert this mapping. If we were able to do that, like things would be very simple, right? So even if you recall the mathematical model that we derived as the linear bicycle model, right? Between the steering input and let's say the yaw rate or the yaw angle, right? So you could observe that although linear, like it was quite an involved model, right? So now imagine, what to say, inverting that model. That is like now you want to write the steering angle as a function of these things, right? It is not going to be pretty straightforward, right? So that's where we need to essentially learn about control theory, and then like we need to figure out how to solve this problem. Okay, in the context of the class of systems that we will study. Okay, so that is very important. Okay, so in fact, one will learn as we proceed as to what are the generic methods that are associated with this class of systems, so that like these tools are applicable not only to automotive systems but any class of systems, any domain, like where you find this class of systems being used, right? So Coming to this mapping, what we would have done in the vehicle dynamics course, we would have solved the problem of synthesis. Okay? That is, if you look at this mapping, y of t equals x of u of t, we would have derived mathematical models, right? Given u of t and y of t, find s. Okay, so that's something we would have done. Okay, in the vehicle dynamics course. Okay, so then we would have done prediction slash analysis. So what do we mean by this? So what is this prediction slash analysis? That is like, now we are given the system mapping yes and the input u. Okay, what is y, right? So we did this also, right, in the vehicle dynamics, right? Is it not? That is, we essentially figure out the responses of various systems, right, to various inputs, right? To essentially give an example, we would have learned about unit step input, unit impulse input, and so on, right? So this will help us in analyzing, what would be the response of the system for various inputs, right? So if you recall, in the vehicle dynamics course, we have solved these two problems primarily. In this particular course, we are going to solve this problem. Okay, what is this problem? This is on control. So what is the problem that we are going to try and solve here? That is, given the mapping yes, the system, and an output that is desired. Okay, we want a particular way of t, find u of t. Okay, so that's going to be the objective of this particular course. Okay, and that is the problem of control. Okay, so as we just discussed, suppose we have a vehicle which needs to be autonomously operated, and we are essentially trying to figure out, what should be the steering angle that should be given as input to maintain a certain heading, right? We are solving the problem of control. Okay, so and that's what we are going to learn in this particular course. Okay, now what are the basic blocks, okay, of this controller, or how do we design this controller? Okay, so essentially we are going to learn about this important concept of feedback. Okay, so what is this feedback? Okay, as the name suggests, so it is essentially figuring out information on the variable that we want to regulate, okay, and using that information to correct our system input such that we get the desired output from the system. So in sticking to the example that we were considering, suppose let us say we want to control the orientation or heading of the vehicle. So orientation or heading of the vehicle is the output of the system, right? And the input to the system is the steering angle. So if this is what we are considering, then what we do in feedback, suppose let us say I want my car to be oriented at around, let's say, 60 degrees, like with respect to some fixed axis, right? Now, what I have to do, if I have to first of all figure out that, or if I want to ensure that my car is oriented along this direction, first I need to figure out what is this orientation at this point in time, right? At this instant of time. Is it not? Because if suppose my car is oriented at an angle of 55 degrees currently, and I want 60-degree orientation. So what I should do, first of all, I should figure out that my car is oriented at 55 degrees, and I should feed back this information to a unit called as a controller, which should then recognize that, look, I am not along my desired orientation, it should say that there is an error between what is desired and what is the actual way orientation, and then it should take corrective action. Okay, so that is the concept of feedback. Okay, so this is very critical. Okay, this leads to what is called as the design of closed loop control systems. Okay, so in general, we can have what are called as open loop control systems and closed loop control systems. Okay, so what is the difference between open loop and closed loop? So if you look at control systems in general, so we can have what is called as open loop control and a closed loop control. So what are these? What is the difference between the two? Let me take a very simple example, right? So let us say we take the ceiling fan, like that we use in our rooms, right? I'm sure like all of us have a regulator knob, which we adjust to different speed settings so that the rotational speed of this fan is changed, right? That is an example of an open loop control system. So what happens is that the manufacturer of the ceiling fan essentially presets or calibrates the position of the regulator to a certain speed, like of rotation of the fan motor shaft. Okay, and then they provide it to us. Okay, so that is an example of open loop control. So we are not going to measure the actual speed of rotation of the fan. Okay, we are essentially going to hope that like the fan works the way in which it is working. Okay, so it was supposed to work, as far as the manufacturer was concerned. So what are the advantages of open loop control? Like it is very simple. It is very what to say, also economical. Okay, so it is not very expensive. It is relatively cheaper, right? And consequently, it has very attractive advantages. But what is the flip side? Suppose, let us say, like there is a voltage fluctuation, okay, in our home or in our office, and the electrical input to the fan changes, okay. So then what happens is that like the fan speed is going to vary, right? It's not going to essentially meet what you and I would have expected, like from the fan in the first place. Or let us say, even if the voltage or electrical supply is very stable, like suppose, let us say I attach something to the fan. Let us say after I install the fan, I attach some light fixture or some other unit to the fan, okay, to the fan rotating element. So now what is going to happen is that the inertia of the mechanical components has increased or changed, right? Now if I provide the same electrical input by the same regulator, I am not going to get the speed for which the fan has been designed. So this is a flip side. But of course, it depends on, like what is the application. See, in our room ceiling fan, I think you and I can still, live with the fact that if the fan has been designed for 100 RPM, and if it rotates at 95 RPM, we can still accept it, all right, and move on. However, consider the example of an industrial fan, okay, wherein there is an exhaust fan which is part of a very important process control system in an industrial plant, and we need to ensure that the fan rotates at 100 RPM for 6 months together. Okay? Then, like what do we do, right? So we cannot tolerate, like a significant variation in the RPM of the fan over a longer period of time. Then what do? We will install a sensor, right, in the fan, which will measure what is the amount of what is the actual value of the angular speed of the fan at each and every instant of time. Then it will provide that information to a control unit. The control unit will compare the actual measurement with at each and every instant of time to what is desired, and then it will take corrective action. Okay, that is what is called as closed loop control with feedback. Okay, So this open loop control mechanism is less expensive, simpler, but cannot tolerate disturbance, but less tolerant to disturbance and system uncertainties and so on, right? Right. So that's a flip side of open loop control. So what we are going to learn in this particular course is closed loop control. So closed loop control has feedback. Okay. Obviously, it is more complex, more costlier, but then like one can tolerate and compensate for disturbance and system uncertainty. All right. So that's the advantage of closed loop. So let me draw a basic diagram. So please look at how I am drawing the diagram. So then we can discuss more about it. Right. So if we take a system or a plan, okay. Now let us say we provide the input to the plan. Let's call the input as some u of t, and we get an output y of t. Okay. So sticking to the problem of controlling the heading angle of a vehicle, let us say the input is the steering angle, output is the heading angle, right? So suppose I tell that I want the orientation or the heading of the vehicle to be, let's say, some fixed value or preset value, right? Then what I provide is the corresponding data. Okay. So what we do is that we provide what is called as a reference input. We will shortly see why it is called reference input. Okay. We provide what is called as a reference input, which is indicated by R of T. The reference input is what we desire, okay, from the overall system. All right. So the reference input will tell us what is expected. Okay. Suppose if I expect a heading angle of 60 degrees, 60 degrees is a reference input. But let's say the actual heading is 55 degrees, then what I do is that I use some sensor to measure the actual heading, and then I feed back this measurement, this information, this data, and then I compare with the reference. So we have a summing junction where we subtract the two signals, okay, R of t and y of t, and we get an error measure. So let me call this error as E of t. So E of t is nothing but the error, which is R of t minus y of t. Okay, so it sort of like gives us an idea between what we desire and what we have actually obtained. Then we pass this error information. Of course, if my desired heading is 60 degrees and if the actual heading is 55 degrees, we can immediately observe that the error is 5 degrees. Okay, so what we do is that we pass this error through a unit called as controller. Okay, and then this controller takes in this error measure. Obviously, it will tell me what should be the steering angle that should be now provided, and it will correspondingly adjust the steering angle. Okay. Then this u of t is called as a control input. Okay. Physically, it's still the same variable, that is the steering angle, but the adjective control is added to the term input just to indicate the fact that now the magnitude of this input is calculated by a controller using the error between the desired and the actual output. Okay, so although the name says reference input, this is what is desired from the system. This is the desired output from the system. Okay, this output is the actual output from the system. Okay, and this problem is what is called as the output regulation problem. Okay, so this is an information I'm giving you. So because we are regulating the output of the system. Okay, so this is what is called as the output regulation. Okay, and we can see that immediately we are having some feedback. All right, so this is a very simple illustration of the entire process. Okay, so I hope it is clear, right, as to what is meant by feedback. Okay, and what are we doing? All right, so this diagram, if I want to put a caption, this is closed loop. Okay, why is it called closed loop? Because we are essentially closing the loop. Okay, you can see that we have measured the actual output and then like we are looping it back to control, to compare with what is designed, and we are taking some corrective action. Okay, so that's why it's called closed loop. Okay, this is a closed loop control system. Okay, control system with, I am purposefully leaving some space. Okay, I am going to come back and write something else. Okay, with feedback. Okay, so I have left some space for adding another adjective, which I'll add shortly. All right, so this is what's called a closed loop control system with feedback. Okay, so as far as terminology is concerned, when we go in this manner, we are essentially going along what is called as a forward path. Okay, so if we go along this direction, we are going along the forward path, and this is what is called as a feedback path. Okay, so we should be aware of all these terms. Okay, what is called as a forward path and the feedback path. Right, so these are some terminology that we should remember. All right. So now, if we look at this particular block diagram, we can immediately observe that at this summing junction, we have subtracted the two signals. Okay, that is R of t and Y of t. Okay, so this is what is called as negative feedback. Okay, so what is negative feedback? At the summing junction, we subtract the two variables, okay, which come, okay, R of t and Y of t. Of course, sometimes we can have what is called as positive feedback also. But by and large, in this particular course, we are going to deal with negative feedback. What is positive feedback? That means that we are going to add both the signals which come into the summing junction. But as I mentioned, in this particular course, we are going to deal with negative feedback. So I am going to add the adjective negative here. Okay. So essentially, I hope it is clear what is negative feedback. Okay. And many times, another point also may come into play. In this feedback part, one may add some other unit. Suppose, let us say we are measuring, we want to get the heading, right? But let's say we have a gyro, like through which I am only getting your rate, okay? But I am interested in your angle. So what do I do if I want to get angle from your rate? What should I do? I should integrate, right? Is it not? Yeah. So if I have to integrate, then what happens is that in the feedback part, the mapping, okay, is an integral mapping, right, in the feedback part. Then we get into what is called as non-unity feedback. So what is this non-unity feedback? That is, in the feedback part, if we do any operation on the output signal, other than multiplying it by 1 and directly providing it to the summing junction, we are dealing with what is called as non-unity feedback. Okay, so I hope it's clear what is meant by non-unity. This is unity feedback. Okay, if we are dealing with unity feedback, that means that the mapping in the feedback part, okay, is going to be 1. Okay? If we are dealing with non-unity feedback, it means that the mapping in the feedback path is not equal to 1. Okay? This may come because we may have, essentially an integral, as we just discussed. Okay, let's say we are measuring yaw rate with a gyro. We want to get the heading angle, and we do an integral operation, right? Then we have a non-unity feedback. Okay, so this is the difference, okay, between non-unity and unity feedback. In this particular course, we will predominantly look at unity feedback, but it is not a given. Okay, sometimes we may look at non-unity feedback. See, sometimes we may want to filter some signals. Okay, because the sensor signal may be noisy, right? Then what happens? Like we will put a filter in the feedback path, and that will lead to a non-unity mapping, right, in the feedback path. So then we will get a non-unity feedback system. All right, so that's something which we should be aware of. All right, okay. So of course, once again, please feel free to stop me anytime. Whenever you have questions, I'm just carrying on with this explanation. So the next thing we need to,
Sorry.
yeah, please go ahead. Yeah.
So the unity feedback is like whatever we are getting if we are just transferring complete as it is. Can we say like that? Without
Negative feedback is this. That is, negative feedback has to do with subtracting the output from the reference input. Okay, that is negative feedback. Negative feedback can be unity negative feedback or non-unity negative feedback. Okay, depending on whether the mapping in the feedback path is 1 or not. Okay. All right. I hope that answers the query. So,
Okay.
yeah. So negative versus positive feedback is one classification of feedback. Unity versus non-unity feedback is another classification. So one can have all four combinations of these two classifications. Okay. So yeah, going forward, see, suppose let us say we stick to the same example. That is like what we are doing is that like we are essentially looking at the problem of regulating the heading of vehicle, right? Suppose let us say I use a gyroscope, right, to figure out the yaw rate, right? However, my gyroscope has some response time, right? So it is also a sensor, right? This is also a dynamic system, right? It is not necessary that the moment I have a stimulus, the sensor should immediately give me a corresponding output. So just take an example. Let us say we have a thermal sensor, right? Or let's say we take the gold standard in temperature measurement, which is to use a mercury thermometer, right? Let's say we want to measure our body temperature. What happens? Like we use a thermometer, we may need to wait for a few minutes, right, before we get the measurement, right? So that means that the sensor will also have its own response characteristics, okay, and it may have its own dynamic characteristics. If that is the case, then we may need to consider what is called a sensor dynamics. That is, if the sensor also responds in a time scale which is comparable to that of the system under study, then we need to consider sensor dynamics. Suppose, let us say, the system responds in a matter of, let's say, hundreds of milliseconds, right? However, we have a sensor that essentially responds in a matter of tens of milliseconds, right? Then we can say that, hey, look, our sensor responds much, much faster, right, than the system per se. And consequently, we will have a much faster response, right? And from the sensor, and consequently, I can neglect sensor dynamics. But however, let us say my system responds in the matter of hundreds of milliseconds, and my sensor also responds in an order of hundreds of milliseconds. Then I need to consider sensor dynamics, right? Is it not, to ensure that I am having an accurate measurement and accurate characterization of the process. Okay, so that's something which is very, very important. Okay, so sensor dynamics needs to be considered in that case. Okay. Similarly, the controller may calculate some input, but that needs to be realized through an element called as an actuator. Right? So let's say, staying with the same example, let us say to get a desired heading, I'm controlling my steering angle, right? Now, if I say, hey, steer my steered wheels by another 2 degrees, right? I need to have some mechanism, right? You may have a rack and pinion mechanism, right, in the vehicle, right, for steering. But however, now the rack and pinion mechanism has to rotate the steered wheels in contact with the ground by, let's say, another 2 degrees. So if I have an electric power steering, then I need to have my electric motor providing that extra effort to rotate the steered wheels by another 2 degrees. Now we ask a similar question. If my system responds in the order of 100 milliseconds, will the time scale of the actuation be in the same order as that of the system, or would it be faster? If I have an actuator which responds much faster than the system's response time, then I can neglect sensor dynamics. On the other hand, if I have my actuator also responding in the same time scale as that of my system, I need to consider actuator dynamics. Right? Is it not? So consequently, this would dictate whether we need to consider sensor dynamics and actuator dynamics in our control design process. Okay, so one can observe that we are keeping on adding elements to this feedback path, right, or the feedback diagram, right, or the closed loop control system diagram that we have drawn. All right. So essentially, we have, to begin with, we had a system or a plant. We wanted to control its output. So we had a feedback process, and we compared the reference input and the actual output. We got an error. We passed it through a controller and got a control input, right? Then we look at whether we have mapping in the feedback path, which is not one. Then we had what is called as non-unity feedback. Of course, by most likely, most of the cases, we are going to consider negative feedback. And then like we also have sensor and actuator dynamics coming to play, right? So when we design this closed loop control system, right? So this is the overall block diagram. Okay. So of course, in addition, we may also have disturbances. So let us say we are essentially dealing with this process of steering the vehicle, right? Suppose let us say there is some side wind, okay, or let us say there is some road banking angle, okay, which may serve as some disturbance on the system, right? Then the question is, can the controller, okay, which we are designing, overcome these disturbances and still work properly? Okay, that is another question that we need to ask. Okay, or in other words, can the controller that we design would it be robust enough to overcome any potential disturbances to ensure that it works the way we expect it? Okay. So, as far as our initial discussion is concerned, we are going to consider a very simple layout, okay? And as we go along, we will look at other aspects like actuator dynamics and so on. All right? So, in this particular course. Okay, so I hope the overall concept, like, or the layout of what is called as a closed loop control system with feedback is clear. All right? So, any questions on this? So what I will do is that like I will stop this lecture here and then we will continue